Okay, now we should be recording. So we know that aptitude is determined by 4 sets of hidden genes. So if any dog has a recessive gene in one of those 4, they'll show aptitude. And the more recessive genes they have, the stronger their aptitude should be. Each sport has its own completely separate gene string. So whatever we're talking about today has to be within one single sport. So I'm gonna just walk through my probability guide method. I know it can be kind of dense and confusing, so I think it might be a little easier for people to follow if they can see it. So basically what you do for this method is you breed 2 dogs, ideally multiple times. You're gonna get better, more consistent results if you have more puppies, and you want to just keep track of how many puppies there were in total and how many of them had the aptitude that you wanted. And then we can use probability to figure out what the most likely genes are for the parents, and then sometimes also the puppies. And there's a lot of chance involved, so you might do it more or less strict than I do, but I'm just going to go through how I use this. So this is the main chart that you're going to want to look at, these pairing probabilities. And this is basically what you would get if you did a ginormous Punnett square with all 4 sets of genes. This is the percentage of puppies that you should get if you have these different pairings. So let me just go through my definitions real quick. So I'm going to refer to, can you all still see my video in the paper? Okay. So this would be a recessive gene. I'll turn my paper too so you can see it. This is a heterozygous dominant gene, and then this is a homozygous dominant gene. And then when I'm going through this, I'm going to use some abbreviations. So when talking about the way that these genes can be paired with each other, if you have 2 recessive genes, I'll just call that a hom-hom pair. If we have a recessive times a heterozygous, I'm going to call that hom, but you should keep in mind that it's really like a hom-het. If we have a heterozygous and a heterozygous, I'm going to call that het. And then if we have dominant and could be anything, I'll call that a dom pair. Hopefully you all can see those definitions. Does that all make sense? Okay, good. If it's ever unclear while I'm talking, just either like speak up or throw something in the chat, and I will try to remember to do that. Yes, aptitude is only these recessive gene pairs. So I have a few dogs that I've already kind of gone through that I'm going to go through again, just so that you all can see. So let's get started. Yeah, let me turn off the screen share for this part. Okay. There we go. Make sure you all can see. So I do 1 page for each male. Yes, Erica, that's the goal. So I write 1 page for each male. So this male is my apocalypse. And I like to write down the parents' genes, and for the case of this example, we're just going to assume that I actually know the parent genes. That's not really set in stone, but I'm gonna just write them down real small, and I'm going to use A's, not B's. I use a lot of different like little tricks to remember things. So if you look at my dog's genes written anywhere, it's gonna be like all kinds of different letters and symbols, and I'll mention some of them, but I'm not gonna go through all of them. I'm just gonna stick with like the typical A alleles that most people use. All right. So if you all can see that, I don't know if that's like clear, but that's my Apocalypse's parents. I'll write everything else bigger because that doesn't look very clear to me. So from this, we know that his genes must be at least one dominant in the first slot, and that comes from his mom here, and at least one dominant in the third slot, that also comes from his mom. And then he has to be carrying a recessive in the third spot, and that comes from his dad. And then I bred him to his sister. So we're going to call her A&L. And we know that because they're full siblings, they're going to have the same genes. I bred them, I think, twice. They had 16 out of 23 puppies with hunting trials aptitude, which is about 69%. All right, so what we know from this is that they both have aptitude, but they can't have their recessive gene in the same location. They can't either both have it at 2 or both have it at 4. One of them has to have it at 2 and one of them has to have it at 4. These are full siblings. So let me screen share again. And we're going to go to the binomial distribution calculator, but first we're going to go here. So what I need to do is find out which of these are possibilities for this pairing. So I'm going to start with the bottom here, 25%. So that's the probability that I want to compare against. The number of trials is the total number of puppies. And the number of events is the number of puppies that had aptitude. And that doesn't look possible. Now, we don't want to look just at the exact number because, you know, if we got 69% and it should have been 25, we want to know what are the odds of getting at least 69%. If it's the other way around and we were expecting 69% and we got 25, we would want to know what are the odds of getting 25 or less. So in this case, we're looking for the odds of getting 69 or more percent, or 16 out of 23, or at least 16, if it should have been 25%. So we want to look down here. And that's a 0% chance, so we'll move up. 43.75. And here you have to put it in as a complete decimal. So that's only a 1% chance. So I'm going to say that that's probably not something that would fit this pairing. I typically use 5% chance as a cutoff. You could use a more lenient percent and say anything that's more than, let's say, 20%, or you could be stricter and say anything that's, you know, at least 1%. What this is really saying is that there's a 1% chance that this would have occurred if it really was supposed to be 43% and we ended up with 69%, because that could happen just by random chance. So let's try 50%. All right, we're getting pretty close here. I'll answer your question the second Sunday. So I'm gonna count this one maybe, and then so we're gonna say that our bottom chance is 50%. So now let's try to find the top of our range. So we know they can't be any more than two Hom pairs because each of them really can't have more than one recessive gene because one of them has to have it in two, the other has to have it in four. And they're ones and threes. They both inherited a dominant allele from their parents. So technically, we can automatically rule out this 4-Hom and the 3-Hom options and just look over here at 85.9%. So now where we're looking has changed. We want to know the odds of getting 16 or less, which is 69% if it was supposed to be 85. That's only a 3% chance, so I'm going to rule that one out. Let's look at 81. All right, that's a 12% chance. So it looks like our range for these guys is this. So what I'm going to do is jot these down. What part of the probabilities do you find confusing, Milton? You can either talk or chat.
Is it okay if I talk?
Yeah, go ahead.
Maybe I just missed something because it's a bit hard to understand for me. But can you show again this calculator and explain why this option like x more or less than 16? Why do you choose this, and what was your logic? I'm familiar with this with binomial distribution in general, but
Yeah.
you seem to get a bit lost in your logic.
Yeah, this is definitely a more confusing step. So basically, you have these probabilities. I bred these dogs. I got 16 out of 23 having aptitude, which is 69%. So if I was going to just look at this, I might say, well, that's closest to 68%, so it's probably this. But because there's random chance involved, I don't know for sure that that's correct. And actually, given what I know about these dogs' parents, that one's definitely not correct. So what I'm using the binomial distribution for, I'm trying to find out what are the most likely options. So I chose a 5% cutoff, so I want to calculate basically all of these and see which of them have at least a 5% chance for me to have gotten 69% out of 23. If it were actually something different, like let's say it was actually supposed to be 78%. If they were a 1-Hom 3 het pairing, I should have had 78% of the puppies, not 69% of the puppies having aptitude. So I want to calculate, what are the odds that it's actually supposed to be 78. So what I did was I calculated just the bottom range, which we found was 50. That had at least a 5% chance. And the top range, which we found, I think, was 81. Did I do 85? Well, let's try 85. No, I did try 85. Yeah, so it was 81 to 50. And so I don't have to calculate these in the middle because I know they're going to be at least 5% chance. So what we looked at here, let me do the 85 again.
And the probability you put your chances from that you just showed. and events, yes, that's clear. And then next options that it shows when you click calculate.
Yeah, so this is your total number of puppies. That's your number of trials, as if you were like rolling a dice or flipping a coin multiple times. The number of
Yeah,
events is
that's pretty
basically the
clear.
number of
Yeah.
And so then when we calculate this, what we want to know, if it really was supposed to be 85% and we got 69, we got a low percent. We got less than what we would have expected. So we want to know
Right.
what are the odds of getting 16 or fewer. So that's where we look at the
Why
16.
16 or fewer?
Because we don't really care about the odds of getting 16 exactly. You could calculate that, but if you include the or fewer, okay, let me say it like this. If you were supposed to get 85% and you actually got 69%, you basically got an unlucky litter. You should have had more aptitude. So you want to know the odds of being that unlucky or unluckier. And then on the other side, if we were to do, let's say, 25%, I want to know what are the odds of getting, 16 or more when I should have gotten way less? What are the odds of being that lucky or luckier? Does that make more sense?
Kind of. I just well, I didn't expect that you use this method for that because I just was to use the chi-square test. Do you know what it is?
You want to use what?
The chi-square test. It's what basically it was Mendel did in his experiments. You have you have the distribution that you expect, and you have your distribution, and there is a formula when you can calculate and say if it seems what you expect or not. No, I'm talking about Punnett squares.
Yeah, so it's this comes from Punnett square. So in this one's kind of easy to think about because if you were to do a one het three dom pairing, draw that one out real quick. So that's too many, but basically in a one het three dom pairing, you have something like this. So do that times, and then these could be anything. So really the only pairs that these are always going to be dom, so your kid is always going to be like this. The only pair that matters here is this. So what you're basically looking at is a Punnett square like this. And then here's where you have your typical, 25% for recessive, 25% for homozygous dominant, 50% for heterozygous. And so we're looking at the chances of getting recessive. So in this case, the one het three dom, where really all that matters is going to be this last pair, you have a 25% chance of getting that recessive. So that's where these come from. A chi-square test. I would have to think about that more, whether you could use that. You probably could, because that would be looking at the frequency. So you probably could use a chi-square to compare to this. I just use the binomial distribution because it's really easy to put into a calculator, and that was kind of what I thought of when I came up with this. But you could probably try that. The Chihuahua test. You can only do it for Chihuahuas. Was there another question that I missed? Okay, just remind me about that Sunday. All right, let me stop screen sharing. And we'll come back over here. So now what we can do is look through these options and see which ones might fit. So again, we've already kind of ruled out options that are more than 2 HOMs because they can only have 2 at most. We know because these line up, they have to have a het pair. So I'm going to go ahead and rule out any that have less than 1 het. Let's see if we have any of those. So we have 2 HOM, 2 DOM. So we know that that can't be true, even though just by probability it was included. And 1 HOM, 3 DOM we can rule out. So that leaves us with some more unknowns. Let's see what else I have put in here. Okay. So I think that's all we can do for them right now. No, we can do more because we know that there has to be one of them having a HOM pair here, one of them having a HOM pair here, which means these can't possibly be het pairs because they would both have to be het. So if one of them is going to have a recessive gene, they can't have a heterozygous gene. So we can rule out the most they could have as het pairs. This could be a het pair. So they can only have 2 at most. So I'm going to go ahead and rule out 1 HOM, 3 het and 3 HOM, 1 DOM. So what we have left now would be 2 HOM, 1 het, 1 DOM. So that would be if both of these were HOMs, this is a het, and then one of these was a dominant. 1 HOM, 2 het, 1 DOM. So if one of these was a HOM pair, one of them was a DOM, these 2 were hets. 1 HOM, 1 het, 2 DOM would be if one of these were HOM, this one's het, and then whichever wasn't HOM was DOM, and this was also DOM. Does that make sense? All right, let me run through the next readings and see if that helps fill things in. The sample sizes are small, but the nice thing about the binomial distribution is that you are calculating the odds, like given what you have. So for example, if I had a smaller litter, let me see what they were before. That looks like 12. Let me just cut this in half. So we're going to say that was 8 out of 11 instead of 16 out of 23 if they only had 1 litter. Now you can see the chances go up a little bit. So it becomes more options are more likely. So for example, we ruled out this one when we had 16 out of 23, but if we only had 8 out of 11 to work with, we would have ruled that in because it's at least a 5% chance. So the more puppies you have total, the narrower you can get that range. But the binomial distribution still tells you like what the chances of getting each thing are. When you get to like litters of like 9 and below, a lot of times if your percent is in the middle like this, it's just anything. It doesn't tell you anything. So let me do our next one. Okay. I'm gonna write and then I'll turn it so you all can see. So the next dog we have that he was bred with, Cyanide. And her genes, oops, nope, we're doing A's. And we're just going to accept this as set because I found it out from another reading. We might have to start a new Zoom meeting if this one times out. Erica, you could do that. You could go and look at these three and check their probabilities and say, oh, this one's most likely, so I'm just going to go with that. I like to be a little more exact, so I keep those as possibilities, but then I use other breedings with different dogs to try to figure it out. So for cyanide, he had 5 out of 9, which is 55%. So let's screen share and look at what 55% could be. So we're going to check 25 against 5 out of 9. And that's almost a possibility. I might write that one down as a maybe. That's very close to 5%. On the top of the list, I'm not going to go down through all of them. I think that would be too much. We know that they have, hang on, I'm on a video. We know that they have one recessive gene here. We know that they don't line up, so we actually do know that his recessive gene has to be here in the 4th place, which makes them a maximum of 2. So let's look at the 2s again. 8, 5, 9. The odds of getting 5 or fewer out of 9 is only 2%. Let's try the next one down, which is 8, 1, 2. That's a 7% chance. So our range is this and maybe that. So let's write these down. But no, I'm going to write them all down and then we'll rule them out just to make this clearer. I'll write a little bit bigger. I'm skipping 4 het every time I write these down because anytime you have 2 dogs with aptitude, they can never be 4 het because you know they have at least 1 recessive. And maybe 1 het, 3 dom. All right, let's stop sharing. If our meeting times out, I will put up a new link. All right, so let's rule out some of these options. So here's what we know. We know that this is a dom no matter what, and we know that this is a dom no matter what. So we know there need to be at least 2 doms. So I'm going to rule out every option that doesn't have at least 2 doms. So that took off a lot. This could be a hom or it could be a dom, but it couldn't be a het. This could be a het or it could be a dom or it could be a hom. So we don't know anything about that. What we do know is that if cyanide has her recessive gene at locus 2 and they didn't have 100% of puppies with aptitude, my apocalypse can't possibly have his recessive gene here. He has to have an A here. And since I know he has aptitude, that means that his recessive gene is here in the 4th place. So because of that, we know that this is a hom pairing, which is the recessive times the heterozygous. And then this could still be hom or dom. We're not really sure. So it could still be 2 homs. We know that there's a hom, so we can rule out this 1 het, 3 dom, because there has to be a hom. We're looking at one to 2 homs. We can't have any hets because these are doms. That's going to be a recessive. That's a recessive. So we can cross out any options with het. And then 2 to 3 dom. So does that all make sense how we got to this point? All right, so now that we know something more about his genes, we can come back and look at A and L, his sister. So because they also didn't have 100%, they can't both have their recessive gene here. So she has to be A here, and she has to have her recessive here. So let's look at these options again. 2 Hom, 1 Het, 1 Dom. These could still both be Homs if these are, carrying. 1 Het, 1 Dom. 1 Hom, 2 Hets, 1 Dom. This could be 1 Hom, 2 Hets, and 1 Dom, or 1 Hom, 2 Hets, and 1 Dom. Could be 1 Hom, 1 Het, 2 Dom. So those are all still possible. We haven't ruled out anything further, but we do know now where these genes are for these two siblings. Now, let's look at another breeding. So Judgment had the same mom and a different dad. And she had 10 out of 11 puppies, with my Apocalypse having Aptitude. The Het and Hom pairs are talking about the way that the breeding lines up, so the parents. By the last female, do you mean cyanide? Yeah, in this case, I knew her genes from previous breedings, and I'm using her to figure out his genes. So let's look up Judgment and see what the possibilities for 10 out of 11 are. I'm going to start high here. So they could even be 4 Hom pairs. That's not actually possible, but they could be, just by probability. I'm going to try 50%. I don't know if we have to go all the way down, but we'll find out. All right, so the chances of getting 10 out of 11, if it was supposed to be 50%, are extremely unlikely. Let's try a higher percent. Now we're getting closer. Let's see what's right above this, 68.2. So there's a 9% chance of getting 90% when it was supposed to be 68.2% if you got 10 out of 11. So basically, it's from here up. So let's write these down. And again, I'm not going to count the 4 Het because they both have Aptitude. They can't possibly be 4 Het.